Hello everyone, my name is Hamid. I'm a PhD student at the Eindhoven University of Technology. Today I want to present a joint work with my supervisors Dr. Reinder Briel and Dr. Peter Kuipers. Here our focus is on Ethernet TSN as an extension of Ethernet AVB standards. TSN aims at providing deterministic services for time-critical applications such as Industry 4, in-vehicle networks, and also 5G, on top of the traditional Ethernet. In this paper, we are interested in services that have two properties, minimum bandwidth reservation and bounded delay. Then let's have a brief overview of TSN. In this picture, you can see the output port of a TSN switch, where packets are grouped into different priority queues. So in order to achieve those properties, TSN should schedule the traffic based on two factors. First, based on its priority, and second, based on some traffic shaping mechanisms. In TSN, credit-based shaping is one of the important flow control mechanisms which is applied to AVB classes, and we use this method in this paper. In this picture, you can have a closer look at the CBS behavior. In CBS, credit decreases during packet transmission and increases when a packet is waiting in the queue for being transmitted. Also, a packet is allowed for transmission only if the class has positive credit, otherwise the packet should wait in the queue until the credit has been recovered again. In TSN, the maximum latency is important, and different analysis has been done in literature to formulate the worst-case response time. For example, this formula is adapted from the eligible interval analysis and shows a relative bound on the delay of a packet. It means that a packet will not be delayed more than a fixed amount of time compared to the situations in which there is no interference. The described behavior was a common interpretation of CBS in literature, but in discussion with some industrial partners, we surprisingly realized that assigning the credit may depend on the interpretation of the TSN standards, and the layer that we are going to implement CBS is important for the worst-case response time analysis. In IEEE standards, packets are data units of physical layer, which consist frames and physical overheads. On the other hand, in TSN, credit is considered to deal with frame transmission rather than the packet. But the worst-case response time analysis performed in literature are basically based on the packet interpretation of TSN standards. So it's clear that when the payload of a packet, I mean the frame part, is being transmitted, credit should drop. But it's not clear what should happen to the credit during the transmission of physical overhead. Should we keep it constant or should we increase the credit? So far, all the papers we have seen consider the physical overhead to be part of the transmission, which makes, as you can see in this figure, the credit simply drops during the entire transmission of a packet. But if we read the TSN standard carefully, it says that the credit should only drop during the frame transmission. So during physical overhead transmission, we could start the recovery phase. Or in another scenario, we can even keep the credit constant during physical overhead transmission. In our paper, we studied these three different interpretations, and also we looked at worst-case analysis in earlier literature and figured out that some of the proofs rely on assumptions that no longer hold in the new interpretations. Then we must revisit those proofs, and we would like to encourage a discussion in the community on how to address this unclarity. Also, we would like to emphasize that it's too early to claim that there is an actual ambiguity in the standard or that the existing analysis cannot be applied at all. But what we have discovered gives us enough reason to check the existing analysis again. This was my presentation. Thank you for your time, and please get in touch if you think this topic is interesting for you.